the video.
Yeah.
I just don't want that they turn off everything and then you cannot have
It's fine.
anything.
Yeah, no, it's all good. Yeah, it should be fine.
We will troubleshoot. Sorry for that.
Yeah, no, it's all good. I get it. Yeah, everyone's working through technical difficulties, so it's all good. Go live. Okay. Okay. So we are live on this. Okay, excellent. Playback. I'll take a slider. Actually, yeah, that'd be great. Yeah, thank you. Awesome. That's awesome. Thank you so much. Is there like anything to drink? Like I could just use a water or something. Okay, yeah, that works for me. Whatever. Thank you. I'll tell you the current thing I'm working on is, so we have YouTube currently streaming, which is good. So it's just capturing this, right? Now the current issue I'm having is Jitsi will not let me turn on my mic so that people can actually hear what's going on.
Why?
I don't know.
Probably because, so I just reconnected.
Yeah, okay. Oh wait, no, they can hear stuff. Okay, awesome. Okay, great.
Just wait.
Yeah. Yes.
Roblox, like they know what it is. What is
It's actually like one of the largest game companies in the world, but like it's primarily they're trying to age it up, but it's primarily aimed at like kids like kind of 7 to 13. But if you have a kid who's like 7 to 13, then they know about it. Yeah, so it's mostly parents and stuff. When I say, they go, "Oh, I hate you guys," but yeah, like it's very popular with kids. Okay, and I just want to see what is the best way. Like this, and then how do we get that? Okay, great. So got that. You're close. Are they? Oh no.
It's mostly
Yeah. Okay. And then. Yeah, that is weird. Because that would be more of a typeface issue than anything else. Yeah, no, you think they would have that, it's like the thing that they do. Everything is hard. Okay, I've got to... Yeah. That's what I found with like not just WeWork, but like all of them is like it's unless you can get an office, it's like it was just too loud for me to work. Just gotta update this. Sorry about that. I hope more people haven't gotten lost. No, this is the first time we've used this venue. Yeah. Hey, how's it going? Yeah. Okay. Yeah.
and still have empty.
I work from home, so I get to have like complete silence. Yeah.
Today.
Yeah. I will say, like, the noise canceling, like, it's gotten pretty good. It's hard to have, like, headphones on all day. Yeah. Yeah.
Hey everybody, we're gonna start up pretty soon. Yeah, everyone grab a seat. Good crowd, awesome. That's all right. I have to sit down for this. First off, I just want to thank everyone for coming to Data Science Lightning Talks. It's been a long time coming. There's been a lot of work in the background from all sorts of people, and I'm just incredibly grateful that we were able to do this again. I would like to thank WeWork for graciously hosting us. Without them, this in-person meetup would not be possible. A round of applause to them. In addition, I would like to thank RJ, stand up RJ. Right here. Yeah, who got us food and security, which was incredible, and also was the connection that got us this WeWork, so thank you so much. This was really nice, you really came through. We are a volunteer-led community focused on improving data science skills within Vancouver and around the world. These talks would not be possible without volunteers. To organize and give talks, we are always looking for speakers and can host talks of any length and will accommodate your busy schedule. This is a great way to get your name out in the community as well as a great learning experience. Please speak to me or any other organizer if you're interested in organizing or speaking. Along with talks, we also have a bi-weekly reading group, so that's going to be not next Wednesday, but the Wednesday after. I believe the 26th. It's on VanillaNet. I don't know what it's about. I know it has something to do with making things simpler in deep learning. You can sign up through meetup.com. We also have a Discord that discusses data science problems and shares job tips. Please join the link from the meetup page and join the hashtag data science channel. All right. Next, we have Laura Thompson, who will give her talk on embeddings. Feel free to raise a hand to ask any questions after she finishes her talk. So just a point of order. These talks are going to be 5 to 7 minutes long, and then we're going to have about 10 to 15 minutes of discussion afterwards, Q&A, anything you want to go ask. Because of our sound situation, you will have to speak up when you're asking a question, because we actually are also streaming live on YouTube. I believe that's everything. So, Laura, yes?
Is it possible to turn off the music?
That is a great question.
Can I also talk about stop playing?
Yes. Yeah.
So there's another meetup that's happening.
You're going to have to talk louder.
So there's another meetup that's happening next week. It's called PyData. I think a couple of the organizers are here as well. That's a talk-driven meetup where we have a speaker that usually presents. Next week we have a talk on prompts and fine-tuning large language models. You should attend. It's next Wednesday, I believe. And we're also looking for speakers all the time. Generally, PyData is more focused on the productionization aspect of, machine learning and data science in general. So if you're interested to talk, either with the voice in the back or the talk.
Ooh, I forgot the most important part. After all of these talks are done, we're going to try to get into Tap and Barrel. I wasn't able to get a reservation, but we'll just see what happens. So if anyone wants to continue the discussion after we close, that would be the place to do it. All right.
Alright, I'll just speak louder and you'll hear me over there. Okay, embeddings. Why? You could already go to the next slide. Everyone's been hearing about embeddings and it's probably because of all this stupid LLM stuff. I'm not going to talk about LLMs because there's so many other reasons to like embeddings. And I've been personally interested in them for years and long before this whole LLM revolution. I still start with what are they with a text example because that's still where most people are coming from. So the whole point of an embedding is you've got this super high dimensional data and that can come from, say, one hot encoding your vocabulary. So the dimension is now the size of your vocabulary, which is enormous. Or it could be super high resolution images, and they say images are only worth 1,000 words. 1,000 words is not that big. So if you wanted to encode that down from the high resolution image, you need to do something fancy. Basically then, you take this high dimensional thing, it's more than just compression though, so what really is it? It really depends on what you need them to do, but ideally you're taking these embeddings in whatever space it is, text, image, sound, video, and you're finding some useful, what we'll call representation, to do a downstream task, whatever that is. Okay, so there's a lot of applications. This top one is just showing how there's graphic properties of word embeddings, but in general embeddings you hope they have some sort of interpretable meaning. They might not though. But here, Leslie, this is something that I always find fascinating when you take images and you can find dimensions that encode glasses or no glasses, balding or no balding, different facial expressions along with different feature axis. This one's for Arnie. A big thing you can do now is just learn embeddings, for instance, of users and items and your recommenders. The system just became so much simpler. Suddenly you learn these embeddings and now something that encodes what the movie is useful for all the parts of your business that has to do with movies. The same with the words, right? Like if people look at text embeddings, what they're useful for, they can look for toxicity in messages, so you can filter emails, you can do sentiment analysis for business, that kind of thing. Alright, so how are they trained? So this is where I'm not going to talk about LLMs at all. Let's go back to sort of a basic neural network. The top here, if you're learning from images, you'll have some sort of convolution layers. The idea then is at the end of your convolution, you've already got what is more or less a feature now encoding of your images. If you want to just abstract that away to something more general, you've got your input dimension. If you create some sort of bottleneck and then force the output and train it on a loss that forces it to match the input, your bottleneck will be some sort of nice embedding. The other thing you can do is, this is contrastive learning, just Google it, I don't have time. Or on networks, same thing. So you've got some sort of target that you want to learn, and then intermediate of your graph neural network will be a layer that will be some kind of embedding, and you can throw away the model that actually learns whatever the target is, the embedding that you actually want to keep. Okay, but how do you evaluate them? Alright, so you have your task that you trained them, not necessarily the task you want to use them for though. So ideally you know what task you end up wanting to use your embeddings on. Say that's for measuring sentiment or for some filter that's catifies all of your pictures and you want to know how catty it is. But ultimately you want to test for your embeddings to know that they're accurate in the task you want. that they're relevant to all the tasks that you need them to be relevant for, but also precise. So supposing you know that they need to break down over the movies, if you look across genres, your embeddings should be quite diverse when you compare across the genres of movies. Okay, and this is the most fun one for me. This is where are the open challenges in embeddings. When I first got into them, I was really keen about running disentangled embeddings just because of my background in physics. But the idea is, say you learn this nice representation, can we somehow force it into a basis where the first bit is, glasses, no glasses, balding or not balding, smiling, not smiling, and like this. I mean, that would be the dream. But there's also progress now in just like in text. What happens if you want to force the different meanings of a word to have different embeddings, or how do you interpret the actual vector encoding of a word if it does have multiple meanings? Right now, GPT-4 is multimodal, so there's a lot of news on this, and this is the idea where you take image and text and potentially video and sound, and you embed them all into the same vector space. So suddenly cat, or a picture of a cat and the word cat are the same coordinate. But of course, embeddings are super useful for applications, and that's the idea of learning from small data sets. There was QLoRa that came out recently. In general, transfer learning, so fine tuning, that kind of thing. And this is just if you want to keep learning. This review at the top left is for a paper from 2012. It's quite old, but it's still actually inspiring ideas for work today. This tutorial at ICML in 2020 is fantastic. I highly recommend watching it. And this post and this series of posts is super awesome. So it's a little bit tangential, but I highly recommend it. I'll share the notes, like the links, you can't see them, you'll be able to access them. Yeah, that's everything.
Nice.
So, questions? Yeah?
What does superposition have to do with embeddings?
Well, that's the idea, actually, maybe that these words with multiple meanings might be superpositions of the underlying two meanings. Like, that's one interpretation. But in general, superpositions support this notion of different features in a lower dimensional space. So each of the bits in your embedding may actually be working with others in superposition to encode more things. Very cool. Worth reading. Get along.
I'm curious, do you think the dynamics of training one of those networks affects the final embedding? If you're a human, you're biased by your earlier experiences, and whatever you learned in that context, you can change the order of the training data, you end up with substantially different embeddings.
Well, for neural networks, it's the opposite, right? They remember the most recent slide test. So, yeah, so presumably, yeah. Also, they're showing that in fine-tuning, you're not so much teaching it new things, but you're amplifying the underlying knowledge towards the task that you need it to perform. So you're suppressing its main knowledge, heightening its ability for its knowledge to the one you care about.
Okay, so it has been 5 years. I'm with someone that says who's super interested in embedding. And I'm also super interested in embedding. I'm just asking, like, what's the most unconventional, fun, weird way of you ever using embedding? Like, is there any cases you can share?
Well, my toy model that I wanted was the spiral in Roll to learn a disentangled embedding automatically without telling it that it was a spiral roll. So trying to figure out how to get the neural network to train Roll.
Okay, you'll be sharing those details later, right?
Yeah, sure.
I have probably a dumb question that has never been clear to me, which is, what exactly is an embedding? Is an embedding only when you reduce dimensionality of an input vector? Is that only when you're allowed to call it an embedding? Or can you also increase dimensions and say, oh, it's just a different representation, so it's an embedding?
So there's actually a link in one of these slides about tabular embeddings, and they definitely increase the dimension. And the idea is that for tabular data, neural networks almost never do as well as boosted trees. But they're showing that if you expand the dimensions by looking at quantile histograms and then embedding those, you can actually start to get better performance than boosted trees with neural networks.
Even in that case, if that I've read that, then wouldn't you say that good? Because if you're quantizing it, you're still releasing dimensionality, right? Because in a way, it originally is over the real domain, right? The real numbers domain. So
Sure, but your features are also over the real domain. So
yeah, that's something that I've never been clear about. When are we allowed to call it?
well, in one of the first slides, I showed a picture actually from differential geometry. So embedding spaces are a way of taking some abstract manifold and embedding into many states. So it's like a simplification to the equivalent dimensions, but something you can work with. So I think that could be
So, I've been using embedding in production, but there's so much I don't understand about them, and I feel very weird about that. And so I'm wondering, you have a slide about like different concepts, and then there's a distance between them. I cannot get my head around why are two embeddings conceptually that are similar are actually close like distance-wise.
Well,
Why
that's
is
the training
that?
method.
Yeah.
Oh, no. I mean, that's definitely how they train them specifically. Like, for faster training, that's the loss. Things that are similar are pushed closer together, and things that are supposed to be not the same are pushed farther apart.
So it's literally what was
It is
represented as
how
meaning in
you are
text.
forcing, yeah.
Why? Somehow it works for like larger
Superpositions people get into. Why are they vectorial? It's mostly just linked.
You get like frustrated things where two things want to be close at the same time, they have to be far away. Or is it because of high dimension that we're at?
That's true. Yeah, it's high enough to mention that they just like it's safer. Yeah, true. Not too deep.
All right. Okay, Sung, you're next. Just give me a little time to readjust and maybe do some
Hey guys,
changes.
just wanted to say sorry, I'll be taking a few photos here and there just for a later page.
Yeah.
I think it's create some content, so then
Yeah.
not gonna, if anybody doesn't like, let me know. Don't want to breach anybody's privacy. Yeah, just let us know in the Discord and I'll make sure that
Yeah. Yeah, just a second. I'm. Yeah, come on over. Grab that. So move this over. Okay. And why can I not make this? Okay. Give me a second here. I have to come down and fix this. Okay, I think I got it. Is it? There we go. Alright. Let me grab the timer and okay, yeah, whenever you want to start.
Yeah, so this will be super great intro to equivariant neural network, whatever that is. And it's a subject, a small subject
usually these days known as geometric deep learning. So it's about utilizing intrinsic symmetry in data. So let's talk about symmetry. So whatever intuitive visual notion you have, I'm sure it's correct. So a shape like this has a rotational symmetry. If I rotate 120 degree, 240 degree, and full 360, I get the same shape. So it has a rotational symmetry. And later to connect with the language of groups. So let's think about the symmetry as this action of rotating itself. So this shape has 3 rotational elements. 1/3 of a full turn, 2/3 of a full turn, and a full turn. Okay.
Sorry. One back.
Yeah. Okay, so I started thinking about the equivariant neural network, and I was playing with this toy example. So it's like an unfolding game. So it's like a super simple AlphaFold. I have like this shape configuration, rectangular loop, and 6 vertices. I'm trying to unfold it. And I'm allowing basically 2 moves. So it's like a buckle and fold it. And allowing these 2 moves, I'm trying to unfold into flat on that. But this is only 6 vertex, so everything's on that. So there are tons of ways of doing it. I think it's, yeah, so, I mean, there are many ways of doing it, but these days, everything you want to do with the neural network. So I want to train neural network how to understand. So it's like Atari game, so reinforcement learning. Let's use the reinforcement learning. So I was setting the Q value, given whatever the configuration state is given, what action is necessary to unfold the configuration. So give it a configuration, let's do Q learning and pick whatever popular. So I just pick the DQN, and later I can pick the Monte Carlo research, like AlphaFold. So you can play that.
Okay.
So, I mean, it's simple enough, so it's quite easy to train. So without any thinking too much about it, it will train for you. I use the DQN for this particular one. So the thing I did was I prepped the data. So I curated the data. So if I just generate any configuration with a 6 vertices loop, but as you can see, there are many symmetric ones, right? I don't know how to say it, but I think if you see it, you know it. A lot of them overlap. By rotating it, I can get the same shape. So I can classify them into basic shapes. So I can cut down the data. It wasn't a big data to begin with, and I cut down even further. So that's why it was. So basically, I probably didn't need any deep learning. Maybe just I could just complete the Q table. But next one. But as you know, if I increase number of vertices, it will get out of hand quite quickly. Right? So even like generating example, I mean, I couldn't just generate all of them. My computer ran out of memory. So for the general case, I guess that's kind of problem. You're trying to do an AlphaFold like question. I guess I would need a Monte Carlo research of not complete solution, but somehow manageable one. But how should I curate the data? I mean, it's becomes quite a headache. So I guess that's what AlphaFold face, I'm sure. So can I make, say, for example, I try to use Monte Carlo research. Can I make my policy neural network, for example, make it more spatially aware? What I mean by that is, if I train my network, so it knows what to do for given stage configuration like this, then when it encounters the rotated version of this configuration, it would be nice my neural network knows what to do without training again. So that's what I mean by spatially aware. I mean, I'm not sure it's the correct way, but I keep thinking how human brain works. But if you teach children how to tie shoestring, different position, they know how to tie the shoestring. So it's something, it should be intrinsic. By changing architecture of neural network, we should be able to program into it. So that's what we mean by equivariant neural network. So once it knows what is optimal action, and when it sees rotational symmetry, it knows what action corresponding to this rotated configuration. So another way of saying it is we have this commutative diagram. So that's basically definition for rotational equivariant neural network. So let's talk about another type of common symmetry. It's a translational symmetry. So this pattern is a translational symmetry. I think you can move left, right, or combine it, diagonal. So it's a translational symmetry. So what kind of neural network is this time? Translation equivariant neural network. Okay. I'm sorry, I have to check.
Yeah.
So it turns out, good old convolutional neural network has a translational equivariancy. So you can check. Translate and convolute is the same as convolute, then translate. So I guess that's one of the reasons, I think it's one of the main reasons convolutional neural network works so well. It handles the translation part. So how about we add, it would be nice to have like a rotational action. It's aware of a rotational action too. So that's kind of situation we encounter in, say, AlphaFold. So it was one of the first application example and probably still the most popular one. So they added this for rotational symmetry. So if we learn how to play on that state, you should know for the other three. Okay, so special case of equivariant neural network is invariant case. That means just the output space, everything is identity. So in
Gotcha. How much do you have left?
I have a couple more slides. I'm almost done. I just read it up.
Okay, my question is, how would you finish off this talk?
It's done actually.
Yeah.
One more slide.
Oh, yeah, do it. Talk about
Okay,
it.
so it was just well, there was a question. How should I finish it? So equivariant neural network is useful, and I think it should be built into whatever. If we want to make our neural network more generally intelligent, I guess. I don't know. Sorry.
Is there a final slide?
Yeah, this is the final slide.
Yeah.
So if you look at how to group convolutional network is implemented, you may think it's just like data augmentation. But depending on what kind of symmetry we are talking about, it becomes we have to think about how we should implement the equivariant convolutional neural network.
Okay.
That's it.
Great. If I may, I'd like to start with a question. So how do you actually encode
especially like the rotational invariance into a neural network? Is it at the embedding level, or is there something else I'm missing?
One of the reasons the old one, the GCNN is popular is it's easier to understand. So basically what they do is it's like you just add more filters, a rotated version of the filter. Yeah. So at first glance, I thought it's not a big deal. It's just like instead of augmenting data, I'm just augmenting filters. But basically, what they are doing is redefining, rethinking about what is actually convolution. If you think about the convolution, it's just translationally invariant convolution. So we are changing instead of translation to rotation and whatever group of your text. And you are redefining the convolution, generalizing. I actually didn't think about it. I was surprised actually. It's all things they can actually talk about like harmonic analysis and all this stuff.
Other questions?
Curious for your DQN for the folding. How did you represent your states? Just coordinates?
So that is the problem with if I want to use E3, that's not going to work because it's a simple case. I just use the x direction minus x direction, y minus y. Yeah. So I didn't use code in the three-dimensional space. So I had to rewrite my data structure if I want to use one of the packages. So that's why I didn't think what the package is.
I'm curious about other types of symmetry that have been folded into this. Is there any like particularly surprising case that you saw? Like the protein folding.
AlphaFold
is
didn't
interesting.
say, but I guess people suspect it should be something called the SC3. What that means is it's any like distance preserving transformation in Euclidean space in 3D. You move the protein, translate it, still same protein. You rotate in any axis, it's still same protein. So that's I guess mostly physics people use it with SC3. So it's orientation preserving Euclidean isometric orientation. So actually there is a package for it, SC3 transformer. So, but the AlphaFold paper I checked and they just say it's equivariant attention transformer, but they didn't quite say what group.
Anything else? Oh,
During your game of like folding the rectangle, like, do you notice certain part? I don't know if you actually like program your architecture to like try to recognize the like translation differences, but do you notice that certain stages changing that suddenly recognize the differences?
Well, I cut out actually 210 of them. So 410 of them, and every vertex there are choice of 72 different actions, and not all of them is applicable, so I can check them. So I just basically because this is like my example from long time ago. I was making games. So at the time I didn't use any neural network, so I have more like deeper shading line using some kind of like computational geometry. But this case, I want to start small, so it's a 6 example. So it's not going to do so. It's
So you apply some you actually like
yeah, it was really quick. It was really quick. It basically completed Q table. So I mean, if you have seen something like this before, but it's traditionally probably used by computational geometry people. It's like unfolding problem. It's like a satellite. It reached orbit. It unfolds the solar panel. So there's subject since 1990s, computational origami. So, but it's not learning approach. So you can find a way, algorithmic way to unfold the shape. But as the number of vertices increase, it's not going to be always doable because you have like a knot. Not everything is unfolded into one knot.
I have a question. So I just want to talk about the things that you addressed. Mentioned the video learning and also another information area. I'm very interested in the information area, but I was thinking about that. It was thinking about how it's related in this field.
So this game is one of my many developed projects. So I didn't know about Monte Carlo research, so it seemed quite fun and local. So I mean, I'm not quite up to date with the computational origami, but computational origami is, I mean, it's a theoretical subject, so it's, a lot of them are related about what cannot be done, right? So yeah, I'm probably I should restart the game, but it will be about the adversarial one, so two nodes and one is trying to create that thing instead of two.
Do you think there aren't existing models that can even on small scale?
Well, I'm sure AlphaFold can do it. But so usually this application of this problem is there are like E3 Python packages, but you have to refigure your data, and you have to probably want to understand how that works. It's not plug and play, and it's subject is to change all the time. All right.
Yeah. All right. Kenneth is up next, but let's just take a short break to get some. I need to work out some tech stuff. But yeah, everyone go grab some food and drinks. Yeah. Could I get another temperature? It turns out the sound is like totally messed up. So this is going to be an in-person only thing, I think. But I'm going to see if there's anything I can do. But thanks. It's like or water, whatever. No, I'm good for right now. Yeah.
Sound like
Yeah, yeah. They don't know what to do, right? But if I can consider this a 64. Yeah, I don't know what I would do. Nobody comes to it. It's like, okay, we're going to get this screwed up.
Yesterday was garbage, you know, but if we get maybe something
All right, everyone, gather around. We're going to have one more either give me like a answer or just say next slide. Okay, all right, everyone. There we go. Yeah, we're about to do the last talk. I'd like to welcome Kenneth. Start whenever you're ready.
Thanks for coming. Thank you all for coming. I'm very excited about this group. So it's been very positive that I'm working with this meeting group. So I'll be speaking today about privacy. So I would begin by going to an overview of space quickly and then focus on information privacy. So I think that will be very exciting too. Maybe you can share slide please.
Sir. Come on. Or save. Just a second. I'm just trying to get rid of it. Cancel. Escape. Sorry, it's hard to do this. Yep. There we go. And this is not against your time, by the way. You're good. There we go. Here we go.
Yeah, so I'll start. What is some mathematical foundations of differential privacy? Then do some case studies like industrial applications, and I'll then discuss multiple ways to achieve it. So overall, like overview of this kind of privacies that achieve differential privacy. Defining it defining it. So what I do some learning and thoughts. So what you want to record in a database, how you protect the privacy of your users when you release these statistics. So there are many ways that can be done. So if you look like differential privacy, you can look at this picture over there. This is a good picture to analyze all the domains we're trying to discuss. So if you look at this, you can see some picture, a man is standing and so is standing there. But there is we added noise within these images. So if you can sample for any kind of distribution and pick out noise. Mainly normal distribution is Laplacian, so it depends on what you're trying to achieve. So multiple distribution is completely different kind of noise you have. So let's say I want to hide the identity of the individuals in this picture. Then read it. So if I hide that identity, the point is why I have a picture with hidden identity and with hidden identities. So let's say I have a surveillance camera and I only want to just count the people that are in this room without even going to because let's say the privacy violations will occur. So maybe I could pass in this image into like another detect the country map. So you can see, if you increase the number of noise, it may end up being almost like this. So that's a maximum noise level. So now this is one option. Let's say, based on the application I want, I will choose the kind of noise I want to have that suits my application. Guaranteeing me a certain level of privacy I want. So there are multiple kind of privacy I'm trying to achieve. So now, let's say I'm trying to achieve the same privacy by just using blurring people's faces. This may require me to first of all identify where the faces are, and then blur on the top of the faces. So, or like reducing downsampling an image. So let's say you have 20 by, let's say you downsample that image. Let's say you have 1, 2, 3, 1, 2, 3, then you represent it as 6 and 6. So some of the faces will no longer be visible because of the reduction in dimensions. The representing function is smaller pixel. That will lead to some privacy. But the point here is, how can I measure the kind of privacy I'm achieving? So, at the target level that I want, with the down pass, the tips, that's like, if I'm doing some statistics, right, preserving some of those results I get. So, a bounded loss of privacy, how can I achieve that? That's what data privacy comes to. So, if you see like homomorphic encryption, so it's okay, that's why I have to explain this. Data privacy is not the same as encryption. So this is the same encryption that like you just have a cipher passing through or not, like another identity. If you look at it, this is pure noise. You can't actually get any trends through it. But in this case, we just added noise, so you could still see trends through it. So if I should explain the difference between homomorphic encryption is like you encrypt data. But now, the encryption space, this is on the group theory, you can perform operations like somatic operation, addition, subtraction, based on addition, multiplication, or Fourier modeling, accept all the operations. So you can actually do operations in the space of encrypted data. And then when you're done with your encryption, you get it, you decrypt. So let me do the distinction before we proceed. So for instance, in an encryption, you have a key that you lock the data. You want some operations to key on the data. But in differential privacy, you don't have a key, but it's just normal noise when you're calculating the noise. So that's the issue. So now, what is privacy now? Privacy is if I have transformed my data, like let's say people have like some information of someone with the date of birth, how much you are paying, your locality. If I remove how much you are paying and still keep the locality when you live in the city, someone can still infer your what's it called, how rich you are, because there are some rich areas and some average areas. So that's something. So you see, so we cannot actually remove fields from our data, just take it like taking our records. So that will still give information if there's codified that captures information underlying the data. So now that is where the information can help us. How can I add noise to those rules at the right amount of noise to achieve a certain level of bounded privacy that it's distorted, but then I can do some aggregate operations on the noisy data itself. So, for instance, if I'm adding noise while I'm preserving the global statistical property of the data. If you look at this, for instance, even though I added noise, you can still see that there is a human being standing there. So, but the point is, if I add too much noise, then it will be almost like this homomorphic encryption. So, but today I'll be focusing on information privacy. So, and then okay, so let's say differential privacy. What does it mean that things are like private? If all your items in the database look the same, then you have maximum privacy. So because there's no way for you to distinguish one from the other. Let's say the police is searching for some suspect, and the suspect looks like 100 other people. It's very hard to identify that individual. In that case, we can say there is privacy, but that individual is blended into the crowd. So that's the kind of privacy we're talking about in this context. Let's say, for instance, this picture. Let's say this is a data point, so data point. So see they look a bit similar, but I'm still able to encode some specific information in each one is there, while still everything is there to some extent. So that's why we are getting to thing known as key anonymity, which I don't want to discuss today. So because that will be going to value best bound probability. So in that case, like if multiple records have similar, they look alike, then there's no way for someone to distinguish between one item and the next. But then if we go and use like Claude Shannon theory of computation when we discuss computation and division. So if you what to describe, this is a property of the big cipher, for instance. The cipher, like the function that encrypts data. Claude Shannon in the seminal work was trying to describe what are properties of those kind of data. So let's say in your differential privacy work, you are making sure you don't make statistical operation difficult to perform. So if you have maximum, that was just totally random data which you cannot learn any information. So you don't want to have like a maximum random data that's fully random that you cannot get any information. You can't see any information. So just that minimum amount of stuff. So now the minimum is this.
1 minute.
Right.
Yeah, 1 minute, yeah.
Okay, that's good to get. Okay, let's say now in diffusion privacy the foundations. So you have like a shuffler, and then this is like your input to the user's data, like the records of the data, and I pass it into the shuffler and get some output that happens when it's added to it. And then these are like each data. So the point is, you see, they should be similar between some bounds. So that's what this just entails. And this one means that if I see the data before I pass it to my randomizer, and then before that I can check what's my gain. So what it means is that let's say I give you a random number generator, and I tell you, is this random generator really random? How can you know that? One option, you could just do like a series of experiments, create one two random numbers, and take an average. Okay, let's go to the next page. So now, this is the basic scheme. So usually you have like a randomizer where you do the test operation. Usually you do that on the client if you want like local privacy or global privacy. Then this is the second also that's optional. Let's say there is information with the order of the data. Like let's say if I'm getting information like by location, I can actually get them, so you can actually shuffle it so that that information is lost. And then this is where you do the aggregation. Like let's say the summation of the counts you gather. Like yeah. So then let's go to the next page. So there are some case studies. So one example, and what I implemented this as part of my research. So let's say I want to save data in the database. And the database, my company, let's say people are actually accessing customer data by looking at what's in the page itself. How can I proceed with saving only the complement of the data so that the user viewing the data will not have any information with data? So I can still query out information from it. So this is we actually represent this like this 3-stat program, and I actually implemented the version of it in this. Okay. So that's one example. Then this is the common one at Apple. So this is like Apple has like when you're using the Apple phone and there is a failure you have, Apple sends your information about that failure for telemetry that places. You don't want to see what's their events they are tracking, or let's say your phone shuts down software. You want to know why that is. Like how many of those kind of things are happening. But they don't want to really know your identity while accessing that information. So I implemented a version of mine of that paper they had. So it's the same way like so this is like you have the dictionary of let's say failure, sudden stop, memory, out of memory, those kind of information. So they want to track it from different users and get an aggregate function. So most of the differential privacy you do then have like aggregate functions to obtain from the set of users that has gone through some noisy, added some noise to distort some information. So there will be some reduction in your accuracy of your estimation, the qualitativity in the papers. But the goal is you will get so those losses can be bounded if you add the appropriate kind of noise. So and then go to this one.
Is this the final one?
Yeah, that's the final one.
Okay.
Okay, so this is like contact tracing. Let's say during COVID, you want to track people's COVID status. And government can abuse this kind of information. So how can the people get to this kind of now COVID because of their proximity to other infected patients without somebody using that information against you? So that's where you can have this kind of differential privacy concept. So they actually works on this ways to go to the website. So this was a kind of a video surveillance system where they want to measure like data analysis. Like, let's say you're trying to see how people are working to predict their next action, like their data analysis. So, but now you see when they added noise on these people, you see we can't identify faces anymore. But we can still do the detection of those stuff. So but now there will be reduction on our accuracy. But we don't really need to know the people on those videos. Let's say we're not trying to track how people are behaving in a place. We don't want them like capture on video camera. This is actually more on camera. So I just read it here. So this is just to show you some of the uses. So what is the appropriate technology to add for the user? So then you can go to this page. So yeah, so I have a blog post out like this is a very rich topic. So it's also attached to this. So even though you have this private information, someone can still link the data you have secondary information just by linking the tables. So the separation linking the text condition attacks is like a reconstruction attacks different kind of attacks. So and you can actually there is a paper reference. So I think this put a lot of papers. So this gives a kind of a very good way to quantify the noise level you want to add in there. And some examples, like some when you have tables or rows that are the question or questions. I think I read a lot on this topic and I'm willing to discuss more about this topic. I'm very excited about it. So what I have written a blog about it. This cannot be covered in one session. So I think this is all I have for now.
So I'll start with a question. So what if a person is unique or very rare along several different axes? Like if they have several features that will make them easily identifiable, do you ever end up where you actually have to drop that person? Because they're too hard to sort of like make, to make indistinguishable from the wider group?
I didn't say that at all. Most of the privacy level, it's worst case privacy they are.
Okay.
So if you look at this paper, there is what they call an ant case and an orb case for rows. So it means like if some part of the attributes in a column is unknown, so you will use like if it's an ant. We use the worst one that exposes the greatest risk as the maximum noise level for all the rules.
Okay.
So I think this paper is one that can help you. You see, then the all case will be like you can guess any one of them.
Right.
So yeah.
Any other questions?
So about adding noise to the images, why can't you just essentially extract statistics from it? So there are like image identification, like people identification algorithms that said that Facebook was like segment anything. You could essentially segment objects out of the image and then store it with just those statistics of it. Like let's say in a video there's like a traffic light and like 60 people walking down the street. You just like Apple does it for our phone. The example that we gave. The database only stores statistics, like how many people were there on the street, or how many balloons were there, or I don't care, how many traffic lights were there. If you do that, you're using less memory, and you're doing privacy as well.
The case of Apple, the privacy is they don't want to describe the user's events from the record of the events. So they want to associate the record from the user. So they don't have like a secondary storage server where they strip out all the IP addresses and the DNS records and then shuffle it. They use the shuffle so that they can only get that aggregate count of the data that they have. So they want to make sure, there are many information that can link information about the record. So you don't want to position it. So the case of the video itself, the premise of the video is like, let's say I want to do gate analysis. What like there's people walking down the street and you want to prevent them from or camera capturing everything. So that's why so the goal is to create that privacy constraints that by design, privacy by design, that by design you cannot really extract more information than necessary. And then we provide you a mathematical framework to bound the noise and the losses in your accuracy when I'm using records. But there will still be some mismatch, like when you make the count. So yes, the distribution of the encrypted data should be similar to the original distribution. Otherwise, you can't have those counts being close at all. So there are ways you can measure those information like distance, like yeah. So yeah. So that's okay.
Just wondering, on your, when you look at the bullet point you had there on this, that seems interesting. So if somebody knows that I was wearing a red and blue hat and you're looking for me, even if you cover the faces, then they would still be able to discover the identified people. So how do you think about the secondary unsecurity?
There is a paper actually released. This ICL last year, 2020. So it's like privacy implications of shopping. So it's trying to identify, they call it inference attack. So it tries to minimize, like on one dimension, let's say you know where someone lives, that information there, and then how you can now prevent the accidents. But there is structural problem. So I didn't discuss it. I don't want to complicate the talk. That paper can give you hints exactly on that. So it minimizes that kind of inference attack. Privacy implications of shopping.
This is sort of fascinating talk. I always wondered like how exactly like Rex said right that we have I would just say so how do you find that now there are more tools in the last application with computer vision and segmentation models and all that stuff to be able to like truly target specific activities? Are there like is it any easier field now? Is it more advanced field like
Okay, so I think I also made a mistake there at the beginning. Those segmentation you are talking about means you have to trust the company to run it on the server somewhere.
No, I mean, I'm doing an open model, some kind of like they run on device.
Okay, there are two kinds of the local one. That's when you do the like you randomize and you run it on the local system, and before you push it, you are not trusting the server to do that operation. So, but most of those segmentation can't really work on this smaller client. So you have to like trust that you are.
Yeah, I'm definitely interested in something that you can run. For example, a Raspberry Pi behind the security camera, or like there's some software that feeds the data. I guess from what I'm hearing, is like those models are not small enough yet. So you're at least still working with more.
But what this has nothing to do with like the model itself, because it's just anything you have. Just add noise to it and bounce the noise, and then if you extract those information, are you bound adding noise to it at some point? So what's the principle is just to achieve privacy. We want to make each record unidentifiable from the output. So let's say just assume it to be like a hash function. All your operation is like so it's only one direction, and you don't want a backward link from the record to the original record. So anyway you define a problem, it doesn't matter. So if that's, but remember you will have some accuracy losses or whatever you're trying to track. But you have to measure it like the losses are incurred, bounding it to the privacy issue. So
what I'm trying to understand is, are you saying that the noise method is the first one? Is that what differential privacy is generally about, and not so much if you're trying to detect faces and then blurring?
Oh no. Differential privacy is just this noise one.
Yeah.
So the other methods like I explained about doing operations on an encrypted data itself. Yeah. So that's a different outside the top. There's also topics like zero knowledge proofs, where actually I'm working on that for the web, but not at the top. So there are many like zero knowledge tools. There's even confidential communication and second knowledge party where you have multiple shares and then collaborate. So if like n-1 is not exposed, it's still secure. Then it's like so you share your key. So there are many security, privacy technologies out there. But for this talk, I focus only on differential privacy because it's so big to cover all aspects.
And differential privacy specifically is about mathematical function that you can apply on the image.
Yes, or any of
or
that.
whatever. Okay.
So yeah, so maybe what you're trying to achieve may be better with a zero knowledge because there's some password protocols like or password management that does zero knowledge. So depends on what you're achieve. So yeah, I think that's I think because I don't have more to
Is there like some safety protocol, something like you're trying to just upload data as much possible as long as it's not like screwing up the
Yes, that's the boundary. Yes. So that's where like if I want to, I think I should explain this like inside. Let's say you do that. It's what they call a conditional. The condition is like you're making the key. This many cipher, the PLK is many part of the key. But the definition is like you are making it harder to retrieve any statistical information. So what in differential privacy, you are adding some noise, and you still want to be reasonable enough not to prevent any form of statistical that the noise will not impede your ability to extract any statistical data out of the noisy input, the noisy output. So it's a balance. So and this like differential privacy gives you a mathematical framework that lets you balance the noise you want to add and the privacy and utility you want to get. So there are like very structured ways to achieve it.
Well, thank you so much. And that wraps up another round of lightning talks. Thank you everyone for coming out. We're going to have to, I think, rearrange some furniture and stuff like that. But we still have a few minutes like before we have to leave. So yeah, without further ado, just go talk amongst yourselves and I'll figure out exactly what we have to do and then we'll go to Tap and Daryl and see if they let us in. So, all right.
Yeah,